Hello and welcome back to Pegasus Rocketry. My name is Mason and this is a video I've been waiting a long time to make. This is the beginning of a long-term project for the channel. I want to build a flight computer. Every flight computer that I've seen has something about it that either makes me uneasy or is just a straight up deal breaker. Some of these things include like the pyro outputs are just fed across the battery. There's no protection, and I've seen instances where it burns up the board, traces are burnt off, it can just cause issues. That's a deal breaker for me. It worked okay in the days of 9-volt batteries. They have high internal resistance, so there was some current limiting there, but in the modern day with LiPos, it just is a problem waiting to happen. Everything works fine until something goes wrong, and then it fails very poorly. Specialized cables, just why? Why do we need specialized cables? USBs are quite common. They're used everywhere. There's no reason to use specialized cables today. It's just quite frustrating. Very, very frustrating. Complicated software updates. They're just a magic trick sometimes. If you've tried to jump pins with tweezers and apply power with your third hand that's coming out of somewhere, it can be tricky and frustrating. I've wasted hours trying to get the timing right at times, and it's annoying. It's annoying. So definitely a sore point. Complicated or inconvenient user interfaces, having to count beeps and map that back to this particular Apogee setting, this particular main. No, you gotta press a button and count the beeps. It's just a hassle. Or having to have your laptop out there in order to program it if you need a last minute change. It's not great. Yeah, there's some options that are better out there, but they've got other issues with them. And this is almost a universal experience, is counting beeps. Counting beeps, counting beeps. Beeps to tell you the voltage, beeps to tell you the programming, beeps to tell you how high you went. It's a whole lot of beeps, and it's not very friendly if you have dyslexia. A lack of protections. There's computers out there that have no reverse voltage protection, so you can blow up your board pretty easily if you aren't paying much attention. There's several out there where there's no overcurrent protection, so if your E-matches happen to get a twist in them, get shorted out, you can cause some damage. There's no ESD protection. Static electricity is a thing. It can damage your electronics. I know some people say they've never seen it in the rocketry world. It's happened to me, and it was super annoying. That's another sticking point. Instead of FETs across a battery, which seems to be the most common option selected, I will have a constant current output. So you cannot pull more than X amps. So I'm not the only one doing that, but it does seem to be in the minority. I will be using USB-C to connect to the device, so no more specialty cables needed to program or pull data from it. I'm going to keep the updating process as simple as possible. No shorting jumpers, no juggling when to apply power, none of that. It should be pretty straightforward and a very simple interface to use. It's going to have a super simple user interface. It's going to have 2 tactile push buttons on it. One to cycle through your Apogee settings. So like at Apogee, Apogee plus half a second, Apogee plus a second, plus 2 seconds. And another push button to cycle through your main settings. So like 500 feet, 600 feet, 700 feet, 800 feet, 1,000 feet, and just loop back around. And here's what I'm most excited about. No more beeping. It's going to tell you. It's going to tell you how high it went. It's going to tell you what is programmed to do. It'll tell you how fast it went, how much acceleration it experienced. It's going to tell you what you need to know. I'm going to include protections to make this as robust as possible. This includes reverse voltage protection, so you accidentally plug your battery in backwards. No problem. You just flip it back around. It works as it should. No damage done. No harm, no foul. I'm going to have the outputs will be current limited, so you can't pull too much current where it causes damage to the board. If E-match gets shorted, no harm, no foul. It pulls the max number of amps that this constant current supply allows, but nothing burns up. No traces get burnt. The computer's fine. Everything stays safe. There will be ESD protection, so you accidentally walk across your carpet in some socks getting ready, and you feel that little zap when you grab your board. No harm, no foul. It should be protected. There should even be some physical protection, so a stray screwdriver when you're in the screw terminal, if it goes stray, you don't damage the circuits. Now, things that are not necessarily better, but just features that I want. I want faster data sampling. I'm looking for a kilohertz or faster accelerometer data. I want to be able to see how much shock I'm putting on the system when the parachute's open. I want to see if I can detect if the charges go off, if the parachutes are even put out before I have to wait to see if they inflate. I'm a bit of a data junkie. I just want to see the data. I'm not looking for bells and whistles. I'm wanting something simple that ensures parachutes are coming out. I want something that can work as a great backup or a standalone device. I want something so easy to use and so difficult to screw up that it becomes the standard recommendation for getting into dual deployment. Now, why am I making this video? I do want to end up commercializing this flight computer. I'm just a person who knows a handful of people in this space. I don't have any brand recognition. I don't have any reputation. If this were to pop up for sale one day with no history, no backstory, why would you trust it? Why would you buy it? Why would you use it? I certainly wouldn't. I'm wanting to document the development process so you can see just a fraction of the work I'm putting into this. I am wanting you to see that I have put it through its paces to the point that I hope you would put faith in it. Now, a little about my background. I graduated in 2018 with my bachelor's in electrical engineering. I went straight into industry out of school, designing circuit boards for industrial measurement and automation, and did that for 3 years. And then I moved to a different company and started designing boards for consumer electronics. Now, where am I at in this project? I've already gotten started. And that's why I've wanted to put this video up for a long time, because I want to give you some info as to where I'm at, but I've got to introduce the project first. So, let me present to you the Pegasus Kiss. And yes, that's for Keep It Simple, Stupid. So this is my first iteration of the board. And it's nice and small. It was okay. There were a lot of issues with it. And yes, I was going down the custom cable route to begin with because I was still figuring things out. But I was started with a set of dip switches. It was going to be 2 switches for apogee settings and 2 for main. It had a beeper. It was pretty straightforward. But when I mentioned physical protection to keep a stray screwdriver from harming your board, this is what I'm talking about, a sort of cover plate that also allows for convenient silk screening that I just wouldn't have space for otherwise. So that's going to be seen in the future. But underneath of that, there we go. It's pretty straightforward, pretty simple. You've got inputs for power and for a switch to cut out power from your pyro circuit, and then you've got 2 outputs, one for main and one for drogue. We have the classic barometric pressure sensor that's good for about 100,000 feet, and a 32G accelerometer, and a little bit of FRAM for storing the data. I'm using a couple just high side switches that are used for switching the outputs on and off. They're current limiting. They're great, easy to use, and that's where Rev 1 went. And that's where this all started. It came to an end pretty quick when I was writing the driver to talk to the pressure sensor, and I was just about done. All I needed to do was divide my output by 100, and once I added that one line of code, I exceeded my program file size, and I couldn't program the part. And so that's when I started working on Rev 2. And here's Rev 2. It looks quite a bit different, doesn't it? You'll notice the high side output switches that were on Rev 1 are gone. This was back when the part shortage was a serious issue. I couldn't get my hands on those anymore, so I decided to go a different route with a switch mode constant current supply. That's all up over here. You'll notice that we've got the USB-C connector now, so getting to a much more user-friendly path. That added a little bit more complexity over here so that your battery can't backfeed into your computer and burn things out there. Added this lovely little tactile switch, which was going to be used to help get you into programming mode. And the output was changed the audio output was changed from a buzzer to an actual speaker. Still using the same pressure sensor, same accelerometer gyro combo, but the memory part, which is supposed to fit right here, well, the footprint was messed up on that, so I could start writing drivers on this and make sure that was all good. Everything was hooked up correctly, and I was able to do that. And that's kind of where this ended, because I couldn't save any data. So that made it a little bit useless at that point, other than validating some hardware. And here's the latest and greatest. This is the third iteration of the board. It looks very similar, other than we got rid of the diff switches. Those hated to be reflowed. They hated my reflow oven. They would burn, they would start to brown, they would lose their tactile switchiness. Once you got a few cycles in there and some fidgeting with it, it just didn't have the quality that I would expect and what I would expect on a product. So those went out the door, and that's when I went to the 2 tactile push buttons. It's much easier to use, especially if you have some thicker fingers. This is much easier to use. I changed the footprint so that my memory fits, and that is perfect. I did change from the barometric sensor that's good up to about 100,000 feet to a smaller little MEMS sensor that's good to about 30,000 feet, 33,000 feet. I did it because of about a $10 cost difference, and if I can save the money, it's going to save you the money too. I still have the pads for the 100,000 foot barometric sensor. I also have pads for a 200G accelerometer. This can go into a pro version later for those who really push the limits, if the demand's there. I just want to point out some design features here. So all the inputs for the power go through some ESD diodes. All the outputs have some ESD diodes before they touch the switching FETs. The USB signals, those also have ESD protection. The exposed ring around the perimeter, that's all connected to ground. So if you start grabbing the board, ground is the first thing you're going to touch. That also helps the circuit board from being cooked from ESD. And when I eventually make a top plate for this, it's going to have the exposed ground as well. That'll be all connected together so that we're protecting this the best we can. We want it to stay safe because it is a critical piece of safety equipment that prevents people from getting hurt. And that's where I'm at in the project. I hope you're as excited about it as I am. And if you think I'm missing a feature, please comment below. And if you want to follow along to see how this develops, please like and subscribe. Have a great one.